Calculation involving unit cell dimensions. We can determine the edge length of a unit cell by X-ray diffraction. We can also calculate the number of atoms per unit cell from the knowledge of the type of lattice. By using these values, we can calculate the density of the solid. Let A be edge length of the unit cell and Z be the number of atoms per unit cell and m be the mass of an atom. Then, volume of the cubic unit cell is equal to A cube and mass of the unit cell is equal to number of atoms per unit cell into mass of an atom. Mass of the unit cell is equal to Z into m. If m is the molar mass of the element, then mass of one atom, m, mass of each atom is equal to molar mass m by Avogadro's number Na. Since density of the material is equal to density of the unit cell, density of the unit cell is equal to mass of the unit cell by volume of the unit cell. Density of the unit cell is equal to Zm by A cube. Now substitute m where m is equal to m by Na. Therefore, density of the unit cell D is equal to Zm by Na A cube, where A is expressed in centimeters, m in grams per mole, and D in grams per cubic centimeter. The density of the substance is the same as the density of the unit cell.
One. Let's solve the problems based on the concept of solid state. The first question goes in this way. A cubic unit cell is made up of three elements, X, Y, and Z. Atoms of X are present at the corners, atoms of Y at the cube center, and atoms of Z at the center of each face. What is the formula of the compound? Let's solve this problem. There are 8 corners in a unit cell. 8 atoms of X occupies them. Therefore, the contribution of X atoms per unit cell is given as 8 into 1 by 8. Addition to that, we also have cube center, which is occupied by only one atom in a unit cell. Therefore, the contribution of Y atom per unit cell is given as 1 into 1. Along with this, we also have 6 faces of unit cell, and the center of each face is occupied by Z atoms. Therefore, the contribution of Z atoms per unit cell is given as 6 into half. By solving the above, we get 1 plus 1 plus 3. Therefore, the ratio of atoms in a unit cell X is to Y is to Z can be given as 1 is to 1 is to 3. Hence, the formula of the compound is X, Y, Z 3. Moving on to the next question. Two elements A and B crystallizes in a cubic unit cell with atoms of A at the corners and atoms of B at the face centers. If 2 atoms of A are missing from the corners and 2 atoms of B from the face centers, what is the formula of the compound? There are 8 corners in a unit cell. Each corner consists of the atoms of A and 2 atoms are missing. Hence, only 6 corners are filled. Therefore, the contribution of A in this unit cell is 6 into 1 by 8, which is equal to 3 by 4. Similarly, there are 6 faces in the unit cell. Each face consists of the atoms of B and 2 atoms are missing. Hence, only 4 faces are filled. Therefore, the contribution of B atoms in the unit cell is 4 into half, which is equal to 2. The ratio of atoms in this unit cell is A is to B, which is equal to 3 by 4 is to 2. On multiplying with the common factor of 4, the above ratio of atoms becomes A is to B, which is equal to 3 is to 8. Therefore, the formula of the compound is A3B8. The next question is, sodium crystallizes in a body-centered cubic unit cell. Calculate the approximate number of unit cells present in 9.2 gram of sodium. Given atomic mass of sodium as 23 gram per mole. Let's move on to the solution. A body-centered cubic unit cell consists of 8 atoms in its corner and 1 atom within its body. Therefore, the contribution of the sodium atoms present in the corner of the unit cell is 8 into 1 by 8, which is equal to 1. Secondly, the contribution of the other atom present within the body of the unit cell is 1 into 1, which is equal to 1. Hence, the number of atoms present in BCC, that is body-centered cubic cell, is 1 plus 1, which is equal to 2. And the number of atoms present in 1 mole of sodium is the Avogadro number of atoms, and we know the value of Avogadro number as 6.023 into 10 to the power 23. And the atomic mass of sodium is 23. Therefore, the approximate number of unit cells present in 9.2 gram of sodium is 6.023 into 10 to the power 23 multiplied by 9.2 gram of sodium divided by its atomic mass, and the number of atoms per BCC is 2. By solving this, we get 1.204 into 10 to the power 23. Moving on to the next question, the question states in this way. In calcium fluoride crystal, Ca2 plus ions are present in face-centered cubic arrangement. Calculate the number of F minus ions in the unit cell. Let's find the solution for this question. Ca2 plus ions of calcium fluoride occupy 8 corners and 6 faces of the face-centered cubic unit cell. F minus ion occupy all the tetrahedral voids created due to the arrangement. Each Ca2 plus ion is surrounded by 8 F minus ions. Each F minus ion is surrounded by 4 Ca2 plus ions. Therefore, the contribution of Ca2 plus ion in this unit cell is 8 into 1 by 8 plus 6 into half, which is equal to 4. And we know that the number of tetrahedral voids is equal to 2 into number of particles present in FCC. Therefore, the number of tetrahedral voids are 2 into 4, which is equal to 8. Hence, the number of F minus ions in the unit cell is 8, and all of them are present within the body of the unit cell. The question is, an ionic compound made up of atoms A and B has a face-centered cubic arrangement in which atoms A are at the corners and atoms B are at the face centers. If one of the atoms is missing from the corner, what is the simplest formula of the compound? Let's find the solution for this problem. In a face-centered cubic arrangement, there are 8 corners in the unit cell. Each corner is occupied by atom A except one corner. Therefore, the contribution of the atom A in the unit cell is 7 into 1 by 8, which is equal to 7 by 8. Similarly, there are 6 face centers in this unit cell. They are occupied by atoms B. Hence, the contribution of the atom B in this unit cell is 6 into half, which is equal to 3. Therefore, the ratio of atoms in this unit cell is A is to B, which is equal to 7 by 8 is to 3. On multiplying with the common factor of 8, the above ratio of atoms become A is to B is equal to 7 is to 24. Therefore, the formula of the compound is A7B24. Let's move on to the problems based on voids in close-packed structure. The question is, structure of a mixed oxide is cubic close-packed. The cubic unit cell of mixed oxide is composed of oxide ions. 1/4 of the tetrahedral voids are occupied by divalent metal A and the octahedral voids are occupied by a monovalent metal B. What is the formula of the oxide? The solution is monovalent metal ion is the metal ion with one vacant position than its original electronic configuration. Same way, divalent metal ion is the metal ion with two vacant positions than its original electronic configuration. The number of octahedral voids is equal to the number of particles present in cubic close-packed unit cell. And the number of tetrahedral voids is equal to 2 into number of octahedral voids. Now, let us consider the number of oxide ions in close packing as n. Then, the number of octahedral voids will be n. Similarly, the number of tetrahedral voids will be 2 into n, which is equal to 2n. As 1/4 of the tetrahedral voids are occupied by divalent metal A, the number of atoms of the divalent metals A occupying the tetrahedral voids are given by 1 by 4 into 2n, which is equal to n by 2. As the octahedral voids are occupied by the monovalent metal ion B, the number of atoms of the monovalent metal ion B occupying the octahedral voids is given by n. The ratio of the number of atoms in the cubic close packing or CCP can be given by A is to B is to O minus 2 is equal to n by 2 is to n is to n. When n is equal to 1, the above ratio becomes A is to B is to oxide ion, which is equal to half is to 1 is to 1. On multiplying with the common factor of 2, the above ratio of atom becomes A is to B is to O minus 2, which is equal to 1 is to 2 is to 2. Therefore, the formula of a compound is A1 B2 O2 minus 2. The next question is, atoms of element B form hexagonal close packing crystal lattice and those of the element A occupy 2 by 3rd of tetrahedral voids. What is the formula of the compound formed by these elements A and B? Solution. Let us consider the number of atoms B in the hexagonal close packing of arrangement as n. Note, the hexagonal close packing of arrangement is also known as HCP. We know that the number of tetrahedral voids is equal to 2 into the number of particles present in HCP. Then the number of tetrahedral void is 2 into n, which is equal to 2n. As the atoms of the element A occupies 2/3 of the tetrahedral voids, the number of atoms in the tetrahedral voids are given by 2 by 3 into 2n, which is equal to 4n by 3. The ratio of A is to B is 4n by 3 is to n. When n is 1, the above ratio becomes A is to B, which is equal to 4 by 3 is to 1. On multiplying with the common factor of 3, the above ratio of atom becomes A is to B, which is equal to 4 is to 3. Therefore, the formula of the compound is A4B3. The question states in this manner: in the mineral spinel having the formula MgAl2O4, oxide ions are arranged in the cubic close packing. Mg plus 2 ions occupy the tetrahedral voids, while Al3 plus ions occupy the octahedral voids. Calculate what percentage of tetrahedral voids is occupied by Mg plus 2 ions. B. What percentage of octahedral voids is occupied by Al plus 3 ions? Percentage of tetrahedral voids occupied by Mg plus 2 ion is 1 by 8 into 100, which is equal to 12.5%. Similarly, only 2 Al plus 3 ions present would be occupying 2 of the 4 octahedral voids available. Therefore, the percentage of the octahedral voids occupied by Al plus 3 ion is 2 by 4 into 100, which is equal to 50%. The question is, in corundum, the oxide ions are arranged in hexagonal close packing arrangement, and the aluminium ions occupy 2/3 of octahedral voids. What is the formula of corundum? Let's write down the given data. When the number of oxide ions involved in HCP is considered as n, the number of octahedral voids will be n. As the aluminium ions occupies 2/3 of the octahedral voids which are available, then the number of aluminium ions occupying the octahedral voids are given by n into 2 by 3, which is equal to 2n by 3. Then the ratio of the aluminium ion is to oxide ion is given by 2n by 3 is to n. When n is 1, the above ratio becomes aluminium ion is to oxide ion, which is equal to 2 by 3 is to 1. On multiplying with the common factor of 3, the above ratio of atoms becomes aluminium ions is to oxide ions as 2 is to 3. Therefore, the formula of the compound corundum is Al2O3. Let's solve the question which involves unit cell dimensions. The question states in this way. A face-centered cubic element with molar mass of 60 gram per mole has a cell edge of 400 picometer, and X-ray studies of its crystals show that the edge length is of 400 picometer. What is its density? The given constant is the Avogadro number Na, which is equal to 6.023 into 10 to the power 23. The solution for this problem is the number of atoms in a FCC is 8 into 1 by 8 plus 6 into half, which is equal to 1 plus 3, which is equal to 4. Then the molar mass of the element is given as 60 gram per mole. Then the element has a cell edge length of 400 picometer, which is 400 into 10 to the power minus 12 meter. To convert this into centimeter, we multiply 400 into 10 to the power minus 12 into 100 centimeter, which is equal to 4 into 10 to the power minus 8 centimeter. Therefore, the volume of the cubic unit cell is 4 into 10 to the power minus 8 to the power 3, which is equal to 64 into 10 to the power minus 24 centimeter cube. The formula for calculating the density of FCC is given by D is equal to Z into M divided by Na into A cube, where Z is the number of atoms, M is the molecular mass, Na is the Avogadro number, A is the edge length. By substituting the value, we get 4 into 60 gram per mole divided by 6.023 into 10 to the power 23 per mole into 4 into 10 to the power minus 24 centimeter cube. Therefore, the density of the element is 6.23 gram per centimeter cube. The question is, density of KBr is 2.75 gram per centimeter cube. The edge length of the unit cell is 654 picometer. Predict the type of cubic lattice to which unit cell of potassium bromide belongs. The given constants are Na is equal to 6.02 into 10 to the power 23 per mole and the atomic mass of potassium as 39 and bromine as 80. The solution for the above question is, from the data we have density is equal to 2.75 gram per centimeter cube and edge length as 654 picometer and the molecular mass is the number of atoms and its atomic mass, which is already given, and hence 39 plus 80, which is equal to 119 gram per mole. And the Avogadro number is Na is equal to 6.023 into 10 to the power 23 per mole. Based on the number of atoms in the unit cell, The type of arrangement can be predicted, whether it is simple cubic unit cell or body-centered cubic unit cell or face-centered cubic unit cell. Now, let us calculate the number of atoms per unit cell by using the formula D is equal to Z into M divided by Na into A cube. By rearranging the terms, we get Z is equal to D into A cube into Na divided by M. Always try to convert picometer into centimeter by using the conversion factor. 1 picometer is equal to 10 to the power minus 10 centimeter, which will make the calculations easy. By substituting the above values in the equation, we get the value of Z as 2.75 gram per centimeter cube into 654 into 10 to the power minus 10 centimeter the whole cube into 6.023 into 10 to the power 23 per mole, the whole divided by 119 gram per mole. After simplification, we get the value of Z as 3.89. By rounding off the above decimals into nearest whole number, we have Z as 4. If the number of atoms per unit cell is 4, then the potassium bromide has FCC center unit cell arrangement. An element X with atomic mass 6 gram per mole has the density of 6.23 gram per centimeter cube. If the edge length of the unit cell is 400 picometer, identify the type of unit cell. Also, calculate the radius of the atom of the element. Let's write down the given data. We have atomic mass of element X as 60 gram per mole and the density of the element as D is equal to 6.23 gram per centimeter cube, and edge length of the unit cell is A is equal to 400 picometer and the Avogadro's number Na as 6.023 into 10 to the power 23 per mole. Now, let us convert the edge length unit picometer into centimeter by using the conversion factor. 1 picometer is equal to 10 to the power minus 10 centimeter. Now, let us calculate the number of atoms per unit cell by using the formula D is equal to Z into M divided by Na into A cube. By rearranging the terms, we get Z is equal to D into A cube into Na divided by M. Now, by substituting the values, we get Z is equal to 6.23 gram per centimeter cube into 400 into 10 to the power minus 10 centimeter the whole cube into the Avogadro number 6.023 into 10 to the power 23 per mole, all divided by 60 gram per mole. After simplification, we get the value of Z as 4. If the number of atoms per unit cell is 4, then the element X has FCC arrangement, that is face-centered cubic unit cell arrangement. But the question doesn't end here. We also have to calculate the radius, and we have the radius formula from the packing efficiency in FCC, which is given by R is equal to A by 2 root 2. On substituting the value of A, we get R is equal to 400 into 10 to the power minus 12 divided by 2 root 2. Therefore, the radius of the atom of the element X is equal to 141.1 picometer. Moving on to the final problem, the problem states in this way. The density of a face-centered cubic element with the atomic mass of 60.2 gram per mole is 6.25 gram per centimeter cube. Calculate the edge length of the unit cell. The solution is, from the data given, we have atomic mass of element as 60.2 gram per mole and the density of the element is 6.25 gram per centimeter cube. For FCC unit cell, the number of atoms per unit cell is always 4. That is, Z is equal to 4. And the given Avogadro's number is Na is equal to 6.023 into 10 to the power 23 per mole. Now let us calculate the edge length of the unit cell by applying the formula D is equal to Z into M divided by Na into A cube. By rearranging the terms, we get A cube is equal to Z into M divided by Na into D. On substituting the values in the above equation, we get A cube is equal to 4 into 60.2 divided by 6.023 into 10 to the power 23 into 6.25. And we get the value of A cube as 6.3968 into 10 to the power minus 23. Let us convert the exponents minus 23 into minus 24, which is divisible by 3. By shifting one decimal point towards the right side of the number, we have A cube is equal to 63.968 into 10 to the power minus 24. Now, by taking the cube root, we get the value of A as 4 into 10 to the power minus 8 meter. This is the answer.
Imperfections in solids. Crystalline solid state is characterized by a three-dimensional periodic arrangement of atoms or ions or molecules in space. Ideally, there should be a perfect order in this arrangement. However, crystals in nature are not perfect. They do not possess perfectly ordered arrangement. This is due to the presence of few impurities or due to dislocation of few of constituent particles from their normal positions. Any deviation from the perfectly ordered arrangement of atoms or ions or molecules in crystal is called imperfection or defect. Defects can be classified into two types: point defects, line defects. Point defects. Point defect can be defined as the irregularities or deviations from ideal arrangement around a point or an atom in a crystal. Line defects. Line defects are defined as irregularities or deviations from ideal arrangement in entire row of lattice points. In this chapter, we will learn only about point defects. The point defects can be further classified into stoichiometric defects, non-stoichiometric defects, impurity defects. Stoichiometric defects. If imperfections in a crystal are such that the ratio between the cations and anions remains the same as represented by molecular formula, the defect is called stoichiometric defect. These defects are also called thermodynamic defect or intrinsic defect. The stoichiometric defects are of two types: vacancy defect, interstitial defect. Vacancy defect. In a crystalline solid, some of the lattice sites are vacant. The crystal is said to have vacancy defect. This generally arises due to the absorption of heat from the surroundings, which results in the decrease in the density of the substance. Interstitial defect. Interstitial defect is caused when some of the constituent particles, can be atoms, molecules, or ions, are present in the vacant spaces in the crystal structure. These vacant spaces are known as interstitial sites, and the particles present in these vacancies are known as interstitials. As the number of particles within the crystal increases, the density of a substance increases. Both vacancy defect and interstitial defects are generally shown by non-ionic solids. Ionic solids do not show these simple vacancy defect and interstitial defects. Instead, they show Schottky and Frenkel defects. Schottky defects. Schottky defect is similar to vacancy defects. This type of defect is created when equal number of positive ion and negative ions are missing from their lattice sites, so that electrical neutrality is maintained. Here, mass decreases while volume remains the same. Presence of a large number of Schottky defect site lowers the density of the solid. Types of compounds exhibiting Schottky defects. Schottky defect is shown by highly ionic compounds which have high coordination number and small difference in the cations and anions. A few examples of ionic compounds exhibiting Schottky defect are NaCl, KCl, KBr, AgBr, and CsCl. Schottky defects maintain the electrical neutrality of the crystal. In sodium chloride, there are about 10 raised to 22 ions in 1 cubic centimeter of sodium chloride, and there are approximately 10 raised to 6 Schottky pairs per cubic centimeter at room temperature. Therefore, in sodium chloride at room temperature, there is 1 Schottky defect per 10 raised to 16 ions. Frenkel defect. If in an ionic solid, a smaller ion, generally cations, goes missing from their lattice site and occupies the interstitial site such that electrical neutrality as well as the stoichiometry of the compound are maintained, this type of dislocation is called Frenkel defect and also called as dislocation defect. This defect is a combination of vacancy defect and interstitial defect. It is a vacancy defect at its original site and an interstitial defect at its new location. Since no ions are missing from the crystal as a whole, Frenkel defects do not affect the density. Frenkel defects are common in ionic compounds which have low coordination number
and large difference in size between cations and anions. Frenkel defects are found in silver halides due to the small size of silver ion and in zinc sulfide due to small size of zinc ion. In pure alkali halides, Frenkel defects are not observed because the ions are bigger than the voids. Impurity defects. So far, we have discussed point defects where there are no foreign atoms. Foreign atoms can occupy interstitial sites or lattice sites in a crystal. Defects in the ionic solids may be introduced by adding impurity ions. If the impurity ions are in a different valence state from that of the host ions, vacancies are created. Let us understand with the help of an example. Consider the crystallization of molten sodium chloride in presence of small amount of strontium chloride, SrCl2. During crystallization process, some of the sodium ions are replaced by strontium ions, Sr plus 2. For every Sr2 plus ion, 2 Na plus ions are removed to maintain electrical neutrality and also creates a cationic vacancy. Similar type of defect and behavior is observed when CdCl2 is added to AgCl. Non-stoichiometric defects. The ratio of combining elements in the compound is different from that required by the stoichiometric formulae. The defects which disturb the stoichiometry of the compound are called non-stoichiometric compounds. These defects are either due to the presence of excess metal ions or excess non-metal ions. Non-stoichiometric compounds are of two types: metal excess defect, metal deficiency defect. Metal excess defect. The solids with metal excess defect contain metal ions in excess to the stoichiometric ratio. Such defect is caused due to anionic vacancies, excess of extra cations at the interstitial site. Metal excess defects due to anion vacancies. In anionic solid, an anion may be missing from its lattice site, leaving a hole which is occupied by an electron to maintain the electrical neutrality. The anionic site occupied by an unpaired electron is called F centers, where F stands for Farbencenter, which is a German word for color center. F centers are responsible for the color of the compound. This kind of defect is shown as alkali halides, such as sodium chloride and potassium chloride. Metal excess defect due to the presence of extra cations at interstitial sites. In this type of defect, metal excess is caused by an extra cation occupying the interstitial site. To maintain electrical neutrality, an extra electron is also present in some other interstitial site. This defect is found in crystals having Frenkel defects. Example: zinc oxide is white or colorless solid at room temperature. But when zinc oxide is heated, it loses oxygen and turns yellow color. ZNO gives Zn2 plus 1/2 O2 plus 2E minus on heating. The excess Zn plus 2 ion gets trapped into the interstitial sites and the released electrons get trapped in its neighboring interstitial sites and maintain the electrical neutrality. Crystals with either of these metal excess defects contain some free electrons, hence, such materials are semiconductors. Metal deficiency defect. This kind of metal deficiency defect is created when a metal ion goes missing from its original lattice site. To maintain the charge neutrality, same metal ion having higher positive charge is added to occupy the vacancies created in the crystal. As this metal ion has higher positive charge, it will occupy only some of the sites to balance the overall charge, and other sites will be left vacant. Example: FeO is mainly found having a composition of Fe 0.950. In crystal of FeO, if some of the Fe2+ ions goes missing, then the loss is compensated by the addition of Fe3+ ions. In this way, though the overall charge is balanced, some spaces will be left vacant in the crystal.